Hey, this is my capstone for CS 5100 Foundations of AI. I am Varun Agarwal and I'm reproducing Kirkpatrick's 1983 optimization by simulated annealing. The idea comes from basically metallurgy. When you anneal metal, you heat it up so atoms move freely, then slowly slow down. So they settle into basically a few low energy structure. Cool too fast and you get a brittle disordered material. That's basically a local optimum. SA does the same thing for optimization. High temperature means the algorithm accepts bad moves. This lets it explore broadly and escape local optima. As temperature drops, it gets more selective and starts exploiting. The acceptance probability for a worse solution is xp negative delta E over T. When T is large, the probability is close to is close to 1, and you accept almost anything. As T goes to 0, the probability goes to 0, only improvements are accepted. That transition from exploration to exploitation is what makes SA work and what hill climbing can't do. The original paper tested on VLSI circuits. I'm testing on three NP hard problems: knapsack, TSP, graph color. Comparing three cooling schedules and MC versus random neighbors. 15 runs per config. So let's start with the first function. These are just the inputs. So over here. All right. So this is basically a modular design. One function, three inputs. Initial solution, cost function, neighbor generator. Swap these per domain and the same algorithm works for any problem. Now let's go to the delta, accept or reject block over here. So the metropolis criterion, basically the better solution always accepts. Worst solution, accept with probability exponential negative delta over t. Say delta is 10 and t is 1000, that's exponential negative 0.01, probability 0.99, almost certain. T equals to 10, exponential negative 1, probability 0.37. T reaches 0.1, exponential negative 100, basically 0. Temperature directly controls how adventurous the search is. Now let's go to the cooling over here. Yeah. So over here, as you can see, there are three schedules. Geometric multiplies by alpha each step. Smooth exponential decay. Linear decreases at constant rate. Log uses T0 over log 1 plus K. This one has a theoretical proof of convergence to global optimum, but only given infinite time. In practice, with T0 of 500, after 12,000 steps, log cooling is still at temperature 53. That's way too hot. Still, we accept bad moves when it should be converging. Geometric at alpha 0.99 reaches about 0.5 by step 7000. That's why it wins. So I'm just going to go to the knapsack now. This was just a brief explanation over here. So let's go to, the first one over here. So there are basically 5 FSU benchmarks, 5 to 10 items known as optimals. Then I'm just going to scroll to the output, right? And over here you can see SA hits 100% on everything. Hill climbing drops to 94.3 on P01 and 97.2 on P06, right? P01 has 10 items and tight capacity. There are local optima where swapping one item makes you infeasible, but the global optimum requires a different subset entirely. SA navigates through those by temporarily accepting worse solutions. T-test gives P equals 0.005. So we can go and check out the plot, right? So all SA bars are at 100. Red Hill climbing dips on P01 and P06. Knapsack is the simplest domain. The interesting results actually come from TSP and graph coloring. So I'm just going to go to TSP to show you that. 1 second. Yeah, TSP is here. Okay. So we want to go to over here. Yeah, perfect. So over here you see the two opt is the standard TSP move, right? Obviously, and we basically pick two positions, reverse the segment between them, remove two edges, and reconnect differently, and can uncross crossings. Now we can just go to the MCMC neighbor. So MCMC computes every edge length, ranks them, picks cut points with probability inversely proportional to rank. Longest edges gets targeted most instead of wasting moves on short edges that are already fine. It focuses on the worst connections. So let's go to the TSP output really quick. Over here, as you can see for over here, so the geometric average again is, I'd say, 30.90, basically optimal. Log gets 38.25, which is kind of 24-ish% worse on the same problem. Same neighborhood, only the cooling changed. And on the second one, we can see it's worse, right? The geometric is 99.1% of optimal. Log only 63.7%. ANOVA, ANOVA gives F over 124, P less than 0.001 for all three instances. So cooling schedule is the single biggest factor. So let's just see the TSP chart over here. Yeah. So the blue geometric bars right at the red optimal line. Green log bars way taller, especially on Ulysses 22 and random 30 where log averages 927 versus geometric at 466. Yep, makes sense. Cool. Now I'm just going to do a small tour visualization as well. You know, the best tours, obviously Burma 14 hits optimal 30.88. Ulysses 22 hits 75.31. Clean tours, no crossings. So now let's go to graph coloring. Quickly. Oh, I'm running out of time. Sorry. Okay, the queen, this one over here, I'm going to explain this. So the queen 5x5, 25 nodes, edges for shared row, column or diagonal, chromatic number exactly 5, 0 room for error, tightest constraint in the project. So again, the MCMC neighbor over here, where's the MCMC neighbor? Yeah, right here. Cool. So this is the most important code in the project, obviously. Two smart things. First, only targets nodes actually hit in conflicts. Scans for nodes sharing a color with a neighbor. Second, picks a color. I'm basically explaining for the whole thing, right? So it picks a color not used by any neighbor. If all color conflicts, picks the one with fewest conflicts. Now comparing that to the random, which picks any node and any color, on queen 5x5 with exactly 5 colors, random moves create as many conflicts as they fix. It's just basically noise, right? So MCMC reduces conflicts faster than the accepting criterion undoes them. So let's go to the graph coloring output over here. So the linear random 0 out of 15. Switch to MCMC, same cooling, 11 out of 15, right? So the neighborhood function alone takes it from the complete failure to mostly working. Hill climbing gets 8, better than random SA, but worse than MCMC because it can't temporarily increase conflicts to reach a valid coloring. Now let's look at the plot for the same. So linear random 13 averages conflicts, log 16, all MCMC versions under 2. That's the difference between blind, perturbation, and domain aware moves. So I'm also gonna show the knapsack. So okay, so let me just say that I'm just gonna go to the heat map really quick. The heat map summary, again, basically green is good, red is bad. Geometric columns, solid green everywhere, and the log random deep red on all the TSP. So I'm also going to show you the convergence curves. Yeah. So again, geometric blue line on TSP keeps dropping to 30. Linear and log plateau at 38 to 40 because temperature is still too high. To wrap up, three findings. Geometric cooling wins everywhere, which fills a gap in the original paper. SA beats Hill, climbing on hard instances through the metropolis criterion. And neighborhood design can be the difference between 0 and 11 out of 15. The paper undersells how important the choice is. Partially reproducible, core algorithm is clear and claims to hold up. But hyperparameter and neighborhood decisions are underspecified, and they matter the most in practice. So this is all my code. Everything is here. So sorry, along the way if I missed a few points, but just to keep it under 10 minutes. But I think I went a little over. But thank you for listening. And if you have any questions, please let me know, and I would love to answer them. Thank you again, Professor, for the semester. Thank you.